Hello and welcome to Chapter 10, Section 1, Lines and Segments that Intersect Circles. Our essential question is, what are the definitions of the lines and segments that intersect a circle? What you will learn is how to identify special segments and lines, draw and identify common tangents, and use the properties of tangents. All right, so the first thing we're going to do is we're going to talk about some of the key vocabulary terms in this entire chapter. This chapter is chapter 10, and it is titled Circles. So, of course, here the first thing we got is a circle. So a circle is the set of all points in a plane that are equidistant from a given point called the center of the circle. So if this here is our center of our circle, all the points here on the circle are the same distance away from the center all the way around. And that's the definition of a circle. So let's keep that in mind. That's going to be very important for us to know. Okay, all the points on the outside of the circle and the circumference of the circle are the same distance away from the center. All right, so what we're going to be talking about next is a radius. Okay, the radius is a segment whose endpoints are the center of the circle and any point on the circle. All right, so what is a radius? A radius is a segment if I draw from the center to any point on the outside, because remember, everything is the same distance. So from the center out to the edge of the circle, that is the radius. Okay, it has to go to the center to any point on the edge of the circle. Next, we have a chord. Okay, so a chord is defined as is a segment whose endpoints are on a circle. Okay, so what that means is that the two edges of our segment, the two ends of the segment, have to be on the edge of the circle. So this is a chord, okay, because we have one endpoint that's on the circle and the other endpoint is also on the circle. So this is called a chord. Okay, next we have the diameter. The diameter is a chord, so the diameter is one of these where it has endpoints on the edge of the circle, but it must contain the center of the circle. So in order for it to be the diameter, it does have to start at the edge of the circle, but it must go through the center point. Okay, so that is the diameter from one side of the circle to the other, and it has to pass through the center. Okay, the diameter is twice as long as our radius. A secant. Okay, a secant is a line that intersects the circle in 2 points. Okay, so this one's a lot like the chord, except for the secant. A secant is a line. So a secant will keep on going forever because it's a line, but it'll intersect the circle at exactly 2 points. So here's 1, here's 2. Okay, so that is a secant. Notice how it's very similar to our chord, except that our chord only stops within the circle. So the endpoints are within the circle. Okay, so this green line here is called a secant. It is a line. And last but not least, we have a tangent. So we've heard tangent when we're dealing about triangles. Okay, but a tangent is a line in the plane of a circle that intersects the circle at exactly 1 point, the point of tangency. All right, so what we need to do here is we need to draw a line that only touches the circle once. Okay, so you can literally draw it from any point. Okay, but the line has to only touch the circle once. Okay, so check that out. All right, so here is an example of a tangent. Okay, because this line only touches the circle at that 1 point right there. That's the point of tangency. All right, and then these are all the important pieces of a circle that we're going to need to know. Let's go ahead and identify some of these segments, rays, and lines as the terms that we just discussed. Okay, so what we're going to do here first is we're going to tell whether the line, ray, or segment is best described as a radius, a chord, a diameter, a secant, a tangent, of the circle C. Okay, and we're going to name the circle C because the center letter that's at the center is a letter C. So we're going to call this circle C. All right, so the first one we're going to do is we're going to identify AC, segment AC. All right, so that's this piece right there, from A to C. So from A to C, it looks like we start at the edge of the circle, and it goes to the center, the direct center. So if we remember from the previous screen, okay, that is the radius. All right, AB, so let's go ahead and, okay, find AB. So from A to B, okay, it is also a segment, and it is at the edges of the circle. Okay, so it could be a chord, right? But if we notice here in the middle, it passes through the center. So this is the diameter of the circle. Next we have DE, ray DE. Okay, so ray DE is this here. Okay, so it looks like it's on the outside of the circle, and then if we take, now we got to take a look at how many times does it pass through the circle, and it looks like it only touches the circle once. Okay, so if we have a line, a segment, or a ray that touches the circle only once, okay, we're gonna call that our tangent. Okay, and last one, we have line AE. So we're gonna start from A. Oops. From A and go to E. All right, so it's a line. It doesn't stop at the edges, so that means that it's going to keep on going. It's a line, and it passes the circle, touches the circle twice, 2 times. It touches the circle once here and once down here. So it could be a chord or a secant, okay? But this is a line, so it keeps on going outside of the circle, so this is a secant. All right, so next we're going to talk about different types of circles, pairs of circles that are coplanar and that contain common tangents. So if in a plane, 2 circles can intersect at 2 points, 1 point or no points. Okay, so if we start here, okay, if the circles have only 1 point where they intersect, so if I draw 2 circles and the circles only touch at 1 point, we're going to call these tangent circles. Okay, because just like the tangent line, see, we have, if we draw a line where the 2 circles cross, okay, that line right there is a tangent to both circles because it only passes through each circle 1 time. Now, if we talk about this next point here, a circle can also intersect 2 times, okay, 2 points of intersection, okay, right? Something like this, where a circle cross each other at 2 different points, okay? And then we can also have points that, circles that do not intersect. So, see how these circles are not touching? Okay. And then we have a special type of circles that do not intersect. These are called concentric circles. So when 2 circles have a common center, okay, so they have the same center point, but they do not touch, they are called concentric circles. Okay, if I draw a line or a segment, and that is, it is tangent to 2 coplanar circles, it is called the common tangent. So that's what we're talking about right up here. So this line that we drew, that is the tangent to both circles, is called the common tangent. Okay, so let's practice drawing out tangent lines on circles. Okay, so the first thing we're going to do is we're going to draw a line, a segment actually, that joins the center of the 2 circles. Okay, and we'll see that this is going to be helpful for us later. So I'm just going to connect the centers of all 3 of these pairs of circles. Okay, and then, okay, it says to tell how many tangents we can draw on the circle, and then we're going to use blue to indicate common external tangents and red to indicate common internal tangents. So we're looking for lines that I can draw outside or through the circle that only touch each circle once. Okay, so we're looking for lines that only touch the two circles one time. So for example, if I draw a line from here, oh, it's not gonna work. Let's do this. Nope. It's a little hard to get it, but all right, let's say that. That is a tangent line right there. Okay, and we're gonna call this an external common tangent. Okay, one because it passes through each circle at one point, and it's called external because this tangent line doesn't cross this segment that we use to connect the centers. Okay, so here's another one. Boom, boom. That line only crosses the circle each one time, so they are common tangents. Okay, and this again is an external tangent because it only touches each circle once and it doesn't cross through the segment that we drew in between the two centers. Okay, so now I'm gonna draw common internal tangents. So an internal tangent is a tangent line or segment that touches each circle once and also crosses through that segment that's connecting the two centers. Okay, so you see how here the tangent line touched the circle once, and then it also crossed that center connecting segment. So this is called an internal tangent. Okay, so then we can draw another one going from top to bottom. Okay, that line there, the segment also crosses one time, and it goes through that center connecting line. So these two circles have 4 common tangents. 2 are internal, 2 are external. All right, so we're gonna go ahead and move on to this next one. Okay, so now let's see. These two circles are connected at one point. Okay, do you see the point where it's connected? Okay, we have these two circles connect here. Okay, so that means that there has to be a common tangent. Okay, when the circles touch at one point, they're gonna have a common tangent line right there, going straight through the 2 points, just like we did on the previous example here. Okay, it's kind of like how this one is. All right, so that's one that we can draw through the middle. And then we're gonna try to draw another. Okay, but no matter how hard you try, you're not gonna get another segment or line that only touches each circle one time. Okay, so that is one. And then we can try to draw some external ones where we can draw them passing through each circle once, like so. 1, 1, and then 1 and 1. Okay, so those are all the segments that we can draw. So we have 3 total common tangents, 2 external, 1 internal. And then these last circles where they overlap twice. Okay, if the circles overlap twice, okay, there is no way that if they overlap at 2 points, there's no way I can draw an internal tangent. Okay, just because they're overlapping 2 times. Okay, so there are no internal tangents, but we're gonna have the same kind of looking external tangents where it crosses the circle one time, one time, one time, one time. All right, so we have circles that do not intersect. Okay, we'll have 4. Looks like we'll have 4. Oops. 4 circles that intersect at one point. Looks like we'll have, at least in this form here, we'll have 3 common tangents, and then circles that overlap twice. Looks like we're gonna have 2. All right, next we're gonna talk about some of the properties of tangents. We have a couple theorems that we're gonna discuss. So first, the tangent line of a circle theorem. So if in a plane, A line is tangent to a circle if and only if the line is perpendicular to the radius of the circle and its endpoint on the circle. So basically what that means is if I can draw a tangent line, and this line right here, M, okay, if that's the tangent line, in order for that to be the tangent, it has to create a 90-degree angle with the radius of the circle. So remember that the radius is from the center to the outside of the circle. So if I have a radius, in order for this line M to be tangent, it has to create a 90-degree angle. Okay, so that's our first theorem with circles and the lines that are related with the circles. And then at the bottom, okay, and we have the external tangent congruence theorem. So if I have two tangent segments from a common external point, the segments are congruent. Okay, so what that means is if I can draw two tangents, right, this is a tangent and this is also a tangent, and these two segments connect at a same point, so in this case we have the point S, then I can say that the segment RS is the same as segment ST. All right, so those are our two theorems. We're gonna use those in the next couple of practice problems. All right, so first of all, we're gonna use the tangent line to a circle theorem. So this one with the 90-degree has to be 90 degrees to verify if the line or the segment is a tangent. Okay, so the question is ST tangent to circle P? So first let's identify ST. All right, so ST is this piece right here, the one that's labeled with the 35. Okay, so we want to know if that segment there is a tangent. And remember, the property said that in order for it to be tangent, it has to create a 90-degree angle with the radius. Okay, so with TP, it must create a 90-degree angle. How can we do this? Well, we just finished a chapter about right triangles. So one thing that we can do is we can figure out if this indeed is a right triangle. So we're going to use the Pythagorean theorem. We're going to do 12 squared plus 35 squared is equal to 37 squared. Okay, so in order for this to be a right triangle, this on the left side has to be the same as 37 squared. All right, so that's what we're going to go ahead and do. We know that 12 squared is 144 plus 35 squared is 1225, and 37 squared is equal to 1369. All right, if we add those two together, they have to equal 1369 in order to be a right triangle. Okay, so if we do 1225 plus 144, indeed we get 1369. Okay, so because this is a right triangle, that tells us that ST is indeed a tangent to circle P. So because triangle STP is a right triangle, segment ST is a tangent to circle P. Okay, something like that as a description for it. All right, now we're going to use that second property, okay, to figure out the radius of the circle. Actually, we won't need that in this one, but so what we're going to do here is we're going to figure out what the radius of the circle is, kind of with that same idea. Okay, so we're going to do the Pythagorean theorem once again, because this tells us that B is the point of tangency. Okay, so remember, if it's telling us that this is the point of tangency, that means that AB is a tangent. That means that this is 90 degrees. So I can use a squared plus b squared equals c squared. I can use the Pythagorean theorem, okay, when solving this equation here. So what we're going to do is we're going to identify our pieces first. So this r, okay, that's our smallest side. So we're going to do a squared. So I'm going to say r squared plus b is our 80 squared, and that's going to be equal to our hypotenuse. And our hypotenuse here is across from the right angle, so that's how I knew that that was it. Okay, but our hypotenuse is two pieces, 50 and r. So what I'm going to do is I'm going to put that in parentheses, 50 plus r squared. So this is all together, this is c squared. Okay, so for the Pythagorean theorem. All right, so then what we're going to do here then is we're going to simplify this here. Okay, and if we think back to our chapter with quadratics, okay, we're going to do r plus 50 times r plus 50. All right, we're going to multiply the binomials. Okay, and that's going to give us r squared plus 100r plus 2500. Okay, and I did that by multiplying this binomial to this binomial. R times r times 50, 50 times r, and 50 times 50. All right, I'm going to bring everything else down. R squared plus 80. All right, so what I want to do here is I want to get the two like terms together. So the two like terms are r squared. I'm going to move this one over to the left side, and you're going to notice how r squared will be canceled out here. That's going to give me 80 is equal to, this is gone, 100 plus 100r plus 2500. Okay, from here we want to get the terms on the same side. So we're going to subtract 2,550. 2,500, sorry, 2,500. Oh, I messed up. There's an error. Okay, stop, take it back. All right, so good. I'm glad I caught this while I was recording. Okay, but you guys see that you guys want to make sure that everything comes down. Notice how that needs to also come down. So we need to figure out what 80 squared is first. 80 squared is 6,400. Okay, so now it's going to make sense. So now subtract 2,500 from both sides. Okay, I'm going to bring down my 100r equals 2, and then I subtract 6,400 from 2,500 to get 3,900. Divide by 100. Okay, and then that means that r is equal to 39, and that is our radius, what we are looking for. Okay, r is equal to 39 feet. And that is correct. All right, and then the last one we're going to go ahead and use the property that we talked about at the bottom, the external tangent congruence theorem. So let's go ahead and look at that problem here. So that property states that if I have two tangent lines, which we do, and it says RS is tangent to circle C at S. So at S, that's where it creates the tangent point, and RT creates a tangent at point T. And because they both connect at R, we know that these two are tangents and that they are equal to each other because of that external tangent property that we talked about. So this one's going to be pretty simple to solve. So what I'm going to do is I'm going to equal both segments. So 28 is equal to 3x plus 4. All right, because these two segments are equal, because they connect at the same point, and they are both tangents of circle C. All right, so then here, all we got to do is solve for x, leave the x by itself. I'm going to subtract 4 to both sides. That's going to give me 24 is equal to 3x. Leave the x by itself by dividing both sides by 3, which is going to give us x is equal to 8. Okay, so this value of x here is 8. All right, that is the end of this lesson. At the end of this lesson, you should have learned about the properties of circles, the different lines that are incorporated in a circle. You should know how to verify the tangent of a circle. You should be able to find the radius, given that the triangle is a right triangle, so that you can use the Pythagorean theorem. You should be able to use the properties of tangents to solve for missing variables and or parts of a triangle. If you have any comments, questions, or concerns, please feel free to leave it in the comment section down below.